Mechanical front-wheel drive, increasing the effectiveness of your tractor. You're able to start field work weeks earlier than your neighbors. Get more work done with more efficient use of tractor horsepower and weight. These claims have been made by all the manufacturers of mechanical front-wheel drive tractors. Any or all of these claims can be proven to be true or false, depending on the specific setup and operational use of the tractor. All of us that have driven a four-wheel drive truck can relate to the benefits of front-wheel drive. Pulling you out of the mud and providing stability in slippery conditions. A four-wheel drive tractor will go places and accomplish tasks that would bury a standard two-wheel drive. There are many outstanding benefits to the design of mechanical front-wheel drive tractors. With this program, we are going to attempt to put mechanical front-wheel drive and its design concept in a new perspective. Not from hearsay, but from actual research studies. We will show the correct or most beneficial setup. We will be explaining the static and dynamic characteristics when these tractors are put through their paces in both a strict testing environment and in actual field working conditions. We will present a rational justification of when to use MFD and when the standard two-wheel drive might be more cost-effective. First, let's take a brief look to the origins and evolutionary nature of this power transmission concept. Mechanical front-wheel drive for the smaller tractors originated in Europe in the mid-40s. Due to the varieties of climatic conditions, soil structures, and topography, there is a continuing regulation in Europe limiting the overall width of agricultural equipment driven on the road. This width limit made it impractical for the farmers to use dual wheels. In order to maintain tractive efficiency, as the tractors became larger, it became necessary to extend the tractive force out through the front wheels. Hence, the mechanical front-wheel drive concept became a reality. The use of MFD became widely accepted throughout Europe. The concept of run-in or pre-run was developed. It was established that the smaller front wheels had to be driven 2% to 4% faster than the primary drive wheels. Over the past 5 years, 70 to 85% of the below 100 horsepower tractors sold in Europe for all manufacturers have been sold with mechanical front-wheel drive. We've learned a great deal about high horsepower mechanical front-wheel drive in the past decade. All the tractor manufacturers in our industry have incorporated MFD into their product lines, with most of the technology for over 100 horsepower MFD tractors being perfected in North America. With this concept, the need for duals can be eliminated, thereby reducing the high horsepower tractors' width and expense. This first area, dealing with dual tires versus singles, deserves some attention. A 14,000-pound two-wheel drive tractor could easily have at any one time a 12,000-pound total rear axle load from the weight of the implement and the weight transfer from the front end. This would be divided by the number of tires, 4 in our case, bringing the total load per tire to 3,000 pounds. 3,000 pounds on each tire causes rolling resistance when traveling through the field, compressing the soil in its track and then pushing the soil out and around the track. The power output necessary to move the tractor can be demonstrated by towing each tractor through a field while monitoring a strain gauge behind the disc. Through this demonstration, we will be able to calculate the horsepower consumed to move a tractor with singles or duals through the same field. First, a two-wheel drive tractor with single tires. This tractor weighs in at 13,455 pounds, approximately 10,000 pounds static weight on the rear of the tractor. In these soft soil conditions, traveling at 4.5 miles per hour, we find that it takes 2,100 pounds of force to move the tractor, which equates to 28 horsepower. Doing the same demonstration with a tractor equipped with duals, it can be determined that the 12 additional horsepower, or a total of 40 horsepower, is needed to propel the tractor. The additional horsepower consumption to move the tractor equipped with duals is necessary primarily due to the increased weight and additional rolling resistance of the duals. This point was confirmed by the North Dakota State University Agricultural Engineering Department when testing both two-wheel drive and mechanical front-wheel drive tractors with singles and duals. In each case, the tractor equipped with duals consumed between 6 and 13% more fuel than the same tractor with single wheels. For lighter jobs, such as planting and cultivating, you can reduce the deep compaction by adapting your two-wheel drive tractor with duals, thereby reducing the ground penetration of each tire. But let's now look at the MFD alternative. First, duals can be eliminated. Less overall tractor weight is needed to attain the same tractive efficiency. Let's analyze this point for a minute. With a mechanical front-wheel drive tractor, 100% of the tractor weight is being utilized, rather than 70 to 85% effective weight of a standard two-wheel drive tractor. The entire weight of the tractor equipped with MFD can be used to develop the maximum tractive efficiency. The front end is constantly pulling, adding to the force exerted on the implement. Rolling resistance is initially felt by the front wheels, with less rolling resistance acting on the rear tires. 30% less on an MFD over a two-wheel drive. The weight and setup of an MFD tractor is paramount in order to achieve top field performance. By examining the effects of loading an MFD unit on the test track, we will be able to dramatically see the performance characteristics of the mechanical front-wheel drive tractor. This tractor is equipped with 18.4 by 38 R1 radial tires on the rear and 14.9 by 28 bias ply tires on the front. The tractor statically weighed in with 60% of the weight on the rear and 40% up front. Under load, a portion of the front weight will be dynamically transferred to the rear. With a 6,500-pound drawbar load, over 1,000 pounds of weight will be dynamically shifted off the front of the tractor to the rear. The recommended tire pressure for the 18.4 by 38s ranges from 16 psi to 24 psi. With the tire pressure set at 16 psi, let's pull a 6,500-pound load and visually monitor the physical characteristics of the tractor. Notice as the load is developed and the weight transfer dynamically shifts to the rear tires are forced to squat under the increased vertical load. As the rolling radius of the rear tires changes, the run-in for the MFD axle is affected. When the rolling radius gets smaller due to the loading on the rear, the relative speed of the front tires or pre-run increases. Torque builds up in the carcass of the front tires when it reaches the tractive limits of the ground. The tire will unwind, causing excessive scuffing and power hop. This can be seen by monitoring a torque meter built into the instrument panel. As the drive line is engaged, the torque output can be monitored by this customized traction performance indicator. By increasing the load on the drawbar of the tractor, the weight is dynamically shifted to the rear and the power hop becomes very evident. This phenomenon is also experienced in the field, reducing tire life and adversely stressing the entire driveline of the tractor. In a situation like the one we've just demonstrated, the operator would experience bucking or a rough ride, low horsepower, and excessive slippage. The solution for this situation could be as simple as adjusting the air pressure in the rear tires. By increasing the pressure up to 24 psi, the squash effect in a working environment is minimized. The object is to maintain as close to a constant rolling radius on the rear tires as possible for heavy drawbar loads. By rerunning the demonstration with the higher tire pressure, we can see an increased tractive effort through a steady pull in the drivetrain. The ride is smoother, tire wear is reduced, and increased field efficiency is realized. The correct setup of a mechanical front-wheel drive tractor is very important to the tractor's operational effectiveness. This tractor shipped from the factory will weigh approximately 4,460 pounds on the front and 8,500 pounds on the rear, or a 35% to 65% ratio front to rear. With a stack of 14 weights and no fluid in the front tires, an operator and a full fuel tank, the front end weight is increased by 1,400 pounds to a total of 5,860 pounds, or an effective weight distribution with 39% total weight on the front and 61% of the tractor weight on the rear. The overall tractor weight is 15,160 pounds, with 24 psi in the rear tires and 18 psi in the front. This tractor is set up for field work. When the tractor is configured in this way, we achieve a static loading of 4,650 pounds per tire. This can be converted by formula or computer graph to establish the contact area of 186 square inches. Divide the total weight on each tire by its contact area to establish the effective ground pressure being exerted by this tractor. 25 pounds per square inch is being exerted on the ground by the rear end of the tractor. In a dynamic loaded situation, taking into consideration the weight transfer characteristics, an additional 550 pounds should be added to the loaded weight of each tire, bringing the contact area up to 212 inches, or an effective ground pressure of 24.5 pounds per square inch. The additional benefit of the mechanical front-wheel drive has a twofold impact on the performance of the tractor. First, the extended footprint of the mechanical front-wheel drive axle contributes an additional 133 square inches of contact area per tire. When taking into consideration weight transfer under load, the front-end contribution is approximately 19 pounds per square inch of additional tractive effort, or 84% additional tractive effort. And second, the tandem wheel effect with MFD causes the majority of rolling resistance to be consumed by the front tires. The rear tires have a track in which to work, a track enabling them to convert more of the rotational energy built up in the driveline to tractive force on the implement with very little additional compaction. The track provided by the mechanical front-wheel drive axle reduces rolling resistance on the rear tires by 77%. The compacted area is no bigger than one tire track. Whereas a standard two-wheel drive tractor with duals would compact twice the area and require additional horsepower to move the unit due to the additional rolling resistance exerted on 4 tires rather than the minimum of 2. There is a considerable amount of controversy over the use of dualed rear tires on a mechanical front-wheel drive tractor. Most of the evidence points to a detraction in field performance when dualing under 140 horsepower tractors equipped with MFD. The two primary deterrents to tractive efficiency are increased rolling resistance of the dualed wheels. This is very close to twice the rolling resistance when compared to the use of singles, and the effect of duals lifting the inner tire out of the already compacted track of the mechanical front-wheel drive. With the over 140 horsepower constant traction tractors, the use of duals might be required to carry the additional load of heavy 3-point mounted implements. Here, it would be advantageous to equip the tractor with the wider 16.9 by 28 front tires, spaced to track between the dualed 18.4 by 42 rear tires. In this way, both rear tires will have equal footing, with the compaction and rolling resistance between the tires held to the minimum. We're not saying that MFD is the ultimate tool for the farming world. There are many instances where the standard two-wheel drive unit would be more beneficial and practical. For example, the modern high-horsepower two-wheel drive tractor being operated primarily in hard soil conditions can effectively transmit its horsepower through single wheels or duals to the drawbar. If there aren't wet spots or a tremendous amount of field variation, the two-wheel drive would be the answer. It would offer versatility and the adaptability needed in a very cost-effective package. The economics of a mechanical front-wheel drive really come into its own when the climate is prone to a wide variation in weather conditions and soil structures. If the landscape is uneven or rolling, the additional investment of the MFD option could pay for itself in the course of a single season when taking into consideration planting and harvesting delays that could have been alleviated with the additional tractive effort and transmission efficiency of the MFD tractor. If an MFD tractor is weighted with approximately 40% of the total weight on the front and 60% on the rear of the tractor, optimum tractive efficiency will be realized. A tractor equipped with MFD can generate greater tractive efficiency with less overall tractor weight than a standard two-wheel drive or a two-wheel drive tractor with duals. The cost of the MFD option can be justified by the ability to ensure seedbed preparation, planting, and harvesting operations on time. A tractor equipped and correctly set up for the MFD is the optimum choice when power and mobility become a necessity.